In the last lecture, we were discussing about the requisite characteristics of a nonlinear two-port network in order to ensure that we get what we want. Our objective is to get power amplification. And we saw that there are certain characteristics in a two-port network that we need from the perspective of incremental Y parameters. And then we were trying to regenerate the requisite IV characteristics, the large signal IV characteristics, or the generic IV characteristics to figure out whether such a network exists, such a device exists or not. And we saw that indeed such a device exists, and you know that you have seen it in your UG curriculum. A device like MOSFET or a BJT, or even if you go back like 50 years, like cathode tubes and so on, I mean, all these devices have similar characteristics, and it's no coincidence that they have been made to have those characteristics, right? In the future, when you have other devices which will be used for amplifications, for example, already people are using FinFETs, then you probably have gate-all-around transistors and whatever. You'll see that all of them will have a similar characteristics. They will all differ from each other from with respect to their underlying physics as to how the carrier transport happens, how the current actually flows. In order to understand that, you will have to take specific courses, physics-specific or device-specific courses where the transport phenomena of the carriers are dealt with. But as far as the circuit designer's life is concerned, all we deal with is IV characteristics. And looking at the IV characteristics, you should be able to tell whether the device that we are interested in will be able to serve our purpose or not. Okay. So again, as I said right at the beginning of this course, probably lecture 1 or even before that MOSFET is a vehicle through which we'll be designing an amplifier in this course. But going forward, probably a few years down the line, or even depending upon which company or industry or research group you join, you might not be using MOSFET in your part. I mean, at least in some maybe 5 years or 10 years from now, right? The device will change. So you should focus more on the approach towards making an amplifier rather than on the particular nuances of the device. The particular nuances of the device will come into picture as the course progresses, because we'll see that there are certain things that a MOSFET, there are certain problems that a device like MOSFET faces, and we'll have to fix those. So, if you look into the op-amp topologies that used to be used when BJTs were in vogue, they were slightly different from whatever they are being used now. The reason being that the issues with the BJTs are slightly different from the issues with MOSFETs. Similarly, the issues of the that will arise from the devices in the future will also be different from the nitty-gritties of a MOSFET. So the details will depend upon what are the characteristics or the final characteristics of the device. But as far as making an amplifier is concerned, this is what it is, right? You have to have Y2 to equal to 0 or very small, Y1 to be equal to 0 or very small, Y21 to be very large, and Y12 to be 0, right? So this is what we essentially want. Understand that, I mean, since many of you will be taking, are probably taking analog circuit course probably for the second time or maybe even the first time, some of these statements that I am making will probably not make sense right away. That's all right. But I hope the statement, you keep it in the back of your mind. I hope the statement makes sense when we end the course, or even when you move out of IIT, go to the industry or design something, right? So it's not as if the stuff that I am talking about in this lecture is only valid for this lecture or till the next quiz. Okay. Okay. So again, the matrix that, I mean, if I go back to our incremental two-port, from there we did a bunch of maths, we got some intuition, and we arrived at the fact that the incremental, this is the full-blown IV, the incremental IV characteristic should have a Y parameter matrix of 0, 0, Y21, which is very high, and 0. And if we apply an input at the input port, we should get amplification at the output port in terms of, and for this particular case, we know, right? So this is equal to minus Y21 times RL times VI will be my output. I mean, again, easy way to think about it is that input impedance is infinity because Y11 is 0, which means this voltage is VI. Y12 is 0, so we don't have to bother about feedback. Y22 is 0, which means there is the whatever current that flows out of that is flowing out of the control source is not getting divided into anything. So the incremental current Y21 times VI flows directly into RL. This is because Y22 is 0, and then it's basically Y21 VI flowing into RL. It gives you minus Y21 RL times VI. That is the output voltage. Okay. So now, then we were trying to recreate the IV characteristics, and we saw that in a device like a MOSFET, if we call this V1 and we call this V2, this is I1, this is I2. What did we saw? We saw that. What did we see? We saw that I1 is equal to 0 always. So we don't have to bother about the I1 versus V1 or I1 versus V2 characteristics. That's a good thing. Less analysis to do. However, we'll have to then, but we cannot do away with the fact that the I2 V2 and I2 V1 characteristics is of importance, and that we'll have to deal with. And we saw that if we are trying to figure out what is the I2 versus V2 characteristics, we know that from our simple device physics courses, I2 versus V2 is kind of a straight line for a range of V2. Not always, but for a range of V2. And we also argued from basic power consumption, the law of power consumption, is the fact that since the stuff inside the box is passive, when I say passive, by the way, what is meant by passive? Can you repeat? Right, that is graphically, but what is, I mean, from the law of power, from the perspective of power consumption, what do you mean by that? Not take any supply. Not take any supply. No, that's not right. Power into something from electrical to something. No, that is also not passive, right? Passive cannot generate power on its own, right? Anything that cannot generate power on its own is passive. If it generates power, it's active. And we know that the only thing that generates power in electrical, parlance is current sources and voltage sources. Nothing else can generate power, absolute power. Okay, so the stuff inside the box doesn't have any source. That's how I have sketched it. So this is passive. Okay, this is okay. So do you think the statement that I just made conflicts with your understanding, or you are okay with that? And then I'll move forward. Okay, great. So since the stuff inside the box is passive, it can only dissipate power. Since it can dissipate power, I can only look at the power that is going in through the ports to figure out how much power is getting dissipated inside the box. So the total power was I1 V1 plus I2 V2. This has to be greater than 0. Since I1 is 0, this goes to 0, which means I2 V2 has to be greater than 0. And if we know that, which essentially means that the I2 V2 characteristics should lie either in the first quadrant or the fourth quadrant. And if I2 V2 is non-zero somewhere in the first quadrant, which means that it has to dive down to 0, otherwise we'll have a problem. It has to pass through the origin, and as it turns out, it indeed does. and let's restrict ourselves to the to the positive half. I mean, to the positive half of the positive values of V2. And now, since we are now getting into MOSFETs, it's probably instructive to get into the details of the IV characteristics of a MOSFET. And as it turns out, in a MOSFET, then again, if I'll not sketch the small signal, I'll not sketch the symbol of the MOSFET. Let me keep it as a nonlinear two-port. As it turns out, your I1 is always 0, so don't have to bother. I2 is equal to, maybe increase this size. I2 has several ways, several modes of operation. So I2 is 0 if V1 is less than certain predetermined voltage, which is called threshold voltage. The I2 is equal to some constant times V1 minus the threshold voltage whole square under certain other condition, and that condition being V2 should be greater than V1 minus threshold voltage. Or there is another region, which is where I2 is beta times V1 minus threshold voltage times V2 minus half V2 squared. This is greater than equal to, and this is when V2 is less than V1 minus threshold voltage. Space. Okay, so this is a type of nonlinearity a MOSFET is. So now let's focus on the IV characteristics, the graphical part of the IV characteristics, to get a better understanding of what to do with it, right? So since we have some plots, we probably need to understand what are the nuances of that plot and what to do with it from the perspective of designing a circuit. Okay. So now let's put some values into it to understand what should we go about, how should we go about doing analyzing this. Let's assume the threshold voltage is 1 volt. Beta, let's say, is 2 milliamp per volt square. I mean, beta by 2 becomes 1, easy to calculate. So let's plot I2 versus V2. By the way, I didn't ask this. I am assuming that all of you are comfortable with basic MOS equations. Is that a fair enough assumption? Okay. So now let's see what is I2 versus V2. So clearly, when I'm plotting I2 versus V2, what assumption I'm making? Assumption I'm making is that V1 is a parameter. V1 is set at some voltage. V1 is not changing, right? So V1 is a parameter. So if V1 is less than threshold voltage, let's say mark V1 is less than threshold voltage. If say V1 is less than 1 volt, what will the plot look like here? Pardon? 0, right? Right. So this is 0. So no problem. Then let's assume V1 is equal to 2 volt, right? So when V1 is greater than, when it actually conducts, when V1 is greater than threshold voltage, then I'll have to see which of these two equations, the other two equations, are valid, right? Whether this condition is valid or this condition is valid. because it looks like I have two types of nonlinearities depending upon whether V2, the relationship between V2 and V1 is satisfied. I mean, it falls under the category of the top equation or the bottom equation. So clearly I'm sweeping V2 from 0 to whatever high value, which means that I'll probably cover both the conditions. So which means I have to find out the boundary. So what will be the boundary in this case? When I'm sketching when I'm trying to sketch the boundary of V2, the boundary will be V1 minus threshold voltage, because the action is happening. All the action is happening at this boundary of V2 equal to V1 minus threshold voltage. So I mark off a point V2 equal to V1 minus threshold voltage for V1 equal to 2 volt, which will be 1 volt. Let's say the mark of 1 volt here. Sketch it somewhere. Okay, so now the easier one to plot is the one which has lesser variables. So the easier one to plot is this one. So let's plot that one. What will it look like? It will be a straight line of value. Y-axis, what will that be? You can calculate and tell me. Beta is 2 milliamps per volt square. Threshold voltage is 1 volt. And V1 is 2 volt, right? So put pen to paper and tell me what will it be? 1 milliamp. And it will be 1 milliamp for the region of V2 greater than 1 volt. Right? So I'll mark off 1 milliamp. To work on my straight lines. Okay, so this is 1 milliamp. And what implication? I mean, what does this plot imply? Without again getting into the physics of the device, this plot essentially says that regardless of the fact that you change V2, the current in the device isn't changing. Right? That's all it says. It's almost like a current source. Right? This is almost like a current source, and the current has been saturated. Current has been saturated to 1 milliamp. And that's why this region is called saturation region of operation, right? So current is saturated to 1 milliamp. So now let's say I still want to stay in this region, but now I say I'll increase V1 to V1 equal to, let's say, 3 volt. Let me sketch 1 milliamp slightly lower, otherwise we run out of space. So now V1 equal to 3 volt. What will it be? What will the new line be? So firstly, the line will change or it will remain the same? Yeah. It will change. Great. So what will the new line be? It will be 4 milliamp, right? 2 minus 1 whole square, so 4 milliamp. Great. So this will be 4 milliamp. So now, till what point will this extend? Will the validity of the curve be? It will be clearly for 2 volt, because we are trying to figure out where is this boundary. The boundary in this case clearly is V1 is 3 volt, VTH is 1 volt, so the boundary is 2 volt. So we mark off 2 volt here. So I cannot extend the curve so far on the left. So this curve will go something like this. And similarly, if let's say V1 is 0.5 volt, sorry, I mean 1.5 volt, say V1 is. Then it will be somewhere here. And this cutoff point will be 0.5 volt. Okay. Okay, fine. So now if I join, let's say if I join these dots, what do you think? I mean, the way I have drawn it looks like a straight line, but it should not be. So what do you think that joining line, what was the equation of that curve? What is that equation following? What is the curve following? Which equation is it following? The second equation essentially, right? This one. I mean, this is following this one. Why? So the other way of asking the same question is, if I pick some other points, let's say I put this point, this point, this point, and join these dots, will the same equation get followed? No, right? So why is that? I mean, current is not changing anywhere, right? So why joining the inflection points is making us follow beta over 2 V1 minus threshold voltage whole squared? Is the question clear or is the question ambiguous? Okay. So it is at the boundary. So what happens then? Correct. It is at the boundary. So because it is at the, it's okay. It's not only sufficient to say that it satisfies both the equation at the boundary, at each of these boundaries, it satisfies the condition that V2 is equal to V1 minus threshold voltage. It's neither less nor small, large. It's exactly equal to V2 is V1 minus threshold voltage. Anywhere to the right of the boundary, V2 is greater than V1 minus threshold voltage. Anywhere to the left of the boundary, V2 is lesser than. So at the boundary, this equation is satisfied. And so one of the reasons we have these piecewise models, right? In physics, I mean, a transistor doesn't know what equation you are using to model its currents and voltages. Just that we make it convenient for our analysis purposes, just to say that in this region, this equation is valid. In that region, that other equation is valid. Okay. So, but essentially, then you have to see what happens at the boundary. Right. So the validity of both the equation, as he pointed out, is true at the boundary. But if you go to the right of the boundary, only one of the equations will be valid. If you go left of the boundary, the other equation will be valid. But the condition at the boundary satisfied both the equations. And that is why, I mean, you can as well say that at the boundary, I can use either equation 1 or equation 2. I mean, either this equation or that equation, both will be valid at the boundary. Okay. Okay, fine. So that is a piece of detail that you should keep in mind. Great. So now, so let's say that I decided to bias my network somewhere here. So say I decided to bias my network here. When I say bias my network, what I'm essentially saying is that in the two-port, I am holding the V2 to be equal to, let's say, I don't know, maybe 3 volt. Okay. And what comment can you make on V1? What am I holding V1 at? No, I'm not holding it at 4 volt, right? Notice I am at this point. So 2 volt, right? Yeah. So V1 is at 2 volt. V2 is at 3 volt. Great. So now I say that I will change the input from 2 volt to By the way, sorry, let me ask you one more question before I jump into this. So what is the, I mean, can you comment on the difference of these plots? In the sense that these plots are, I have sketched these plots for increments of V1 equal to 1 volt. Correct? So is the distance between the plots same? They are clearly not same because our device is nonlinear. It's quadratic in this case, so the difference is doubling every time you increase by equal amount. Okay, fine. So now I say that instead of 2 volt at the input, that is V1 equal to 2 volt, I go to 2.1 volt. Okay. So then what should we do? Going by the same thing that we have been doing till now. I want to figure out what is this new I2. So when it was 2 volt, the I2 was 1 milliamp. I want to find out what is the new I2. From graphical methods, what should I do? Given that I know the equations and all. Okay, it's simpler than that. There is no two curves. Uniform. There is, why would you want to? Why is the second curve? Which other second curve would you like to superimpose? Right. So V1 equal to 2.1. If I sketch the V1 equal to 2.1 curve, what will it look like? It will probably be higher than that 1 milliamp curve, right? So this will probably be somewhere here. Okay. So the difference between these two will be, I write out the two equations for V1 equal to 2.1, V1 equal to 2, subtract, I will get something that will be the difference. Now, given that we know what the small signal analysis equivalent is, instead of doing all those things, can you comment on quickly, how can I figure out what is the difference? Note that I haven't said that the input goes from 2 volt to 5 volt. I purposefully said that the input goes from 2 volt to 2.1 volt, with the assumption that 0.1 volt is small signal. Right? So what will be that difference? Can you tell me the expression, then we'll get into the details. Okay, so, but the difference cannot be transconductance. Difference has to be current, right? I'm trying to figure out how much the curve will shift upwards if I go from 2 volt to 2.1 volt at the input port. Pardon? Okay, so I think you do the, sketch the full drone, right? VGS minus VT whole squared minus that. That's fine. So let's do that. Let's do that also. So what I presume you have done this. So the current in case of I, when V1 was 2.1 volt, is 2.1 volt rather, is 1 milliamp per volt square times 2.1 minus 1 whole square, which is 1.21. And when this was 2 volt, it was, this is 1 milliamp. So difference is 0.21. Right? So that is fine. So this will be 0.21. But the reason I'm harping on this is that not always you will have these situations where you can easily figure out what is that increment in current. And for that, we have developed a framework of incremental analysis. So given that we know what the incremental analysis is, can you comment on what that, using incremental analysis, what will be the difference? Somebody says transconductance. Who said transconductance? Yeah. So can you comment on that? Excellent. Right. So what is this? What am I doing? I mean, in a very layman terms, what am I doing? I'm saying that I'm sorry, I didn't sketch it at the right place. So I'm saying that for a fixed value of V2, in a quiescent state, which means for incremental V2 equal to 0, I'm trying to figure out what will be the increment in I2. Right? That in plain English, that's what I'm asking. Is that statement clear? For a fixed value of V2, I'm trying to figure out how much has the current changed, which means in an incremental domain, I'm asking what will be the increment in current given that the increment in V2 is 0. And given that there has been an increment in V1. Correct? So what am I asking? In plain English, I'm asking, find the increment in I2 with respect to V1 when V2 equal to 0. And what is that? Can you speak up? I heard somebody say something from this side. Right. So we essentially want del I2 over del V1. You are wanting del I2 over del V1, given that V2 is constant, which essentially means that in incremental sense, I'm asking I2 over V1 when V2 equal to 0. Right? But I mean, this is okay. So not exactly this. I'm asking the change in I2, which means I have to multiply with del V1. Which means I have to multiply with V1. So del I2 over V1 is Y21, and V1 is the increment that I'm looking for, right? So what is V1 in our case? What is the increment? 0.1 volt, right? So V1 is 0.1 volt. What is Y21? For Y21, what do you need to figure out Y21? Which equation are you looking at? This one or this one? Middle one or the bottom one? Okay, somebody said bottom one. I mean, I want to understand why. How many of you think it's the middle one? How many of you think it's the bottom one? Or let's say the top one? No? Sure? Okay. So why bottom one? Okay, let me ask you the folks who think that it is the middle one. Why not the bottom one? Okay. So we are operating in the region where the current is not changing. Right? So clearly the middle equation is wrong. Okay. So fine. So if I want, so the full IV characteristics in this case, if the transistor is biased in that saturation region of operation, is I2 is equal to beta by 2 V1 minus threshold voltage whole square. And I1 is equal to 0. So this is my F1, F2. So what is Y21? Well, this should be pretty straightforward, right? Simple differentiation. Right. So del I2, del V1 for a fixed V2, right? Which essentially in this case means beta V1 minus threshold voltage. For V1 is equal to what? For V1 equal to, I have two voltages here to deal with, 2.1 volt and 2 volt. Which V1 should I replace it with? Why not 2.1 volt? Exactly, right? So what was the genesis of incremental analysis? You have to find out a quiescent point and then see increments on top of it. Right? What was now the decision of quiescent point can depend on the designer. I mean, I start off with something, then I'm trying to see increment on top of it. So in this case, I wanted to start off with 2 volt and then trying to see the increment on top of 2 volt. I mean, it's not because 2 volt is a round number. Okay, so sometimes it can as well be we have some weird numbers which has to be the quiescent point. In that case, that will be the quiescent point. In this case, we are making the maths easy, so we took 2 volt to be the quiescent point. So which means what is Y21 in this case? Beta is what, 2 milliamp per volt square, right? This is 2 milli, 2 minus 1. This is 2 millisiemens. So what will be the increment in current? Or rather I1, right? I1, which is delta I1, I2, sorry, delta I2, which will be equal to 2 millisiemens times 0.1 volt, which means 0.2 milliamps. So with the brute force analysis, we got 0.21, right? So the difference between these two were 0.21. And with incremental analysis, we got difference is 0.2. Why do you think there is a difference? Right, we have neglected the square terms. Right, when we are doing incremental analysis, we are replacing the nonlinear stuff with a tangent, right? So we are essentially saying the higher order terms can go to hell. Right? So we like to use our only linear model. And because when you're using a linear model, you will get some error always, right? So the question that is often posed to a designer is that error sufficient? Is that error good enough? So that we'll have to see, right? But the framework of small signal analysis is you can neglect that error to the first order. Okay, fine. Any questions? Okay, fine. So let me redraw this. So this region again, for the sake of completion, is called saturation. And this region is called linear region or triode region of operation. Okay, so this is as far as I2 versus V2 is concerned. Let's turn our attention to I2 versus V1. So by the way, if we are biased here, right? If we decide to bias our transistor in that region, when I say we decide to bias our transistor in that region, means the relationship between V2 and V1 is such that we fall in that region, then clearly this equation is valid. This equation is valid. So what's the problem with that equation? Why is that not a good place to bias? So let me write it out to make that point. So in linear or triode region, the current equation that is valid is So what is so bad about this? Output current depends on V2. Fine, that output current depends on V2. So what? I agree, output current depends on V2, but so what? Small increment in I2 for is that true? Because let's say I am somewhere here. So we agree that the curves are continuous. There is no discontinuity. Let's say I am somewhere here. Just to the right, I have saturation. Just to the left, I have linear. Right? So since the models are continuous, I would presume the increment with respect to V1 will be same, isn't it? So why again, I come back to the question, why should this be a problem? Why is this not a good place to bias? Yes, you said that it depended on V2. I agree. But so what? Distortion will come much later. I wanted to figure out whether this can be a decent amplifier if I bias in linear region. What is the load? Okay. Output resistance will affect the current. Can you elaborate on that?
It depends on V2, right? So V2 is voltage across output.
Right. If the V2 changes, the current changes. Right? Yes, you are on the right track. That is, in fact, a very good explanation. But I'm looking for something else. I'll come back to that. Something much simpler. It is related to what is said. The load will, the current is dependent on V2, load will affect the current. All are right statements. They are not, none of the statements are incorrect. But I'm trying to get at the heart of the issue. Why is this a problem? Slope, right? So what? Slope, correct. V1 dependent is there, right? The equation is dependent on V1. Pardon? Yes, it is dependent on V2. So what? So why do you not want? All of you are saying the same right statement. None of you are saying the wrong thing. But I am trying. It's still not a heart of the issue. Perfect. So ultimately, we want Y22 to be 0. What is Y22 in this case? Firstly, what is the Y22 in saturation? 0. Slope is 0, right? So Y22 0. What is Y22 in this case? For a sum V1Q, right? So which in this case will be what? Right? So clearly their Y22 is not 0, which means if you go back to the incremental model, if you go back to our incremental model, right? So what was the output side of the incremental model? This was, right? You had Y22 and you had input side and you had RL. So you wanted Y22 to go to 0, but if you bias your transistor in the linear region, your Y22 will not be 0. There will be current division between Y22 and RL. So you are losing part of the current. You are losing part of the incremental current to its own internal resistance. Right? This is not a separate resistance that you have put, but the transistor by virtue of its operation in linear region has a internal resistance, which is modeled as Y22. So the incremental current that is coming out, right, can be of the same order as the saturation region current equation. However, most of the current or part of the current will flow into Y22 and not go into RL. And hence you will lose out current. And hence you will lose out output voltage, incremental output voltage, and hence you will lose out on amplification. Okay, fine. So that is the main reason why you would want to you wouldn't want to bias your transistor in linear region if you are planning to design anything as an amplifier. However, let me since we are talking on this, I know it's a slight digression from the topic that we are discussing, but let's assume that I still want to. Can you think of an application where I want to bias my device in a linear region, given that Y22 is this? It has nothing to do with amplifier. Just let your mind go wide. Given that Y22, the equation of Y22 is whatever you are seeing on the screen, can you think of an application of using the device in linear region? So what is this? If Y22 is that, if I inverse it and get into the resistance domain, so what is R? Incremental R is 1 over beta. Perfect, right? So this looks like a variable resistor, right? Sometimes you would want to change the resistance. What you do typically in a lab, if you want to change the resistance, you have a potentiometer and you turn the screw, right? So what is the equivalent screw in this case? In this case, there are multiple screws, right? You have one is V1Q, other is V2. Now, depending upon how would you want to bias it, right? So in most cases, you would like to say that, I mean, if you, again, without getting too details into this, let's assume that you have biased it in such a way that it's deep into triode. What I mean is by deep into triode is somewhere here. You're biased somewhere close to here, not at zero, but away from zero. So in that case, I can make the approximation that this is equal to beta V1Q minus threshold voltage. Right? If V2 is much lesser than V1Q minus threshold voltage is that knee, right? So this is that V1Q minus threshold voltage. If I am way left of that, then I can say that this is equal to the resistance is V1Q minus threshold voltage. And let's say I want to use this device as some voltage variable resistance, then this device probably has a third terminal, which is V1Q. And I can quick change that V1Q to change the resistance. This becomes your that third terminal of a potentiometer, which you use to change the resistance. So this is one very good application of transistors biased in linear region. Okay, fine. So again, I digress. Let's come back to amplifier. So we plotted I2 versus V2. Now I am plot I2 versus V1. So the obvious thing is to first say that what is the threshold voltage? Our threshold voltage, let's say, is 1 volt in our case. So anything below threshold voltage, it doesn't really matter, right? Everything is 0, at least as per our model. So now let's say again we have biased it like this. Okay, V2 is, let's say, 3 volt. So V2 is a parameter in this plot. I'm changing I2 with respect to V1. V2 is a parameter, V2 equal to 3 volt. So now when I start off, when I'm just above 1 volt, what is the region of operation of the transistor? Is it linear, saturation? Is it linear? Why? How will you establish? I'm just above this, right? Somewhere in the vicinity of 1 volt to the right side of it. So what test will you perform to establish whether it's linear or saturation? Yeah, right. So V2 is the question that we'll ask is V2 is greater than V1 minus threshold voltage or not? Or in other words, since I'm varying V1, right? So it's better to ask in this way. Is V1 less than right? So in this case, V2 is a parameter. So V2 is 3 volt, threshold voltage is 1 volt, 4 volt, right? So is V1 less than 4 volt? Clearly, yes, which means it will be in saturation. Okay. So it will be in saturation, and the saturation current equation holds. And as I keep on increasing V1, can you comment on, is it going towards linear, away from linear? It is going clearly towards linear because I have to ensure that V1 is less than 4 volt, right? So if I mark up 4 volt here, so this guy will probably keep on increasing till 4 volt, and then it will enter linear region. And what will the curve look like once it enters linear region? Pardon? Straight line, right? So because ultimately, again, we are focusing on this equation, sorry. Focusing on this equation now. So with respect to V1, this is a straight line, right? So with a slope of V2, correct? Straight line with a slope of V2. So this guy is happening. This guy will go something like this. Now let's say I decided, any questions on this? Okay, so now let's say I decided to change the parameter, that is I change V2. to go from V2 equal to 3 volt to, let's say, V2 equal to 4 volt. What will the new curve look like? Or let's say V2 equal to 2 volt, right? 2 volt might be easier to plot. So V2 equal to 2 volts. So what will this new curve look like? Let's start off again from threshold voltage, from 1 volt. So let me give you options, multiple choice. Will this go like this, or it will follow the, it will go up. I mean, let me use different colors also. So will it be the black one, red one, or yellow one? Sorry, green one. Black one. Why black one? Okay, right. So the saturation region current is not dependent on V2. Correct? Saturation region current is not dependent on V2. So this will clearly will be it will follow. But will it follow all the way to 4 volt? It will now follow up to 3 volt because ultimately this is the boundary. Right? So you'll have still maybe 3 volt, it will follow. And then this will diverge. And then this will go. So the new line, the new straight line, can you comment on the slope of the new straight line? Will it be higher than the higher? It will be higher or lower? It will be lower because the slope is V2, right? So it will clearly be lower. Okay, fine. So that is as far as I2 versus V1 is concerned. But why am I interested in the I2 versus V1 plot at all? Other than to establish whether I am sitting in linear or saturation region, what is the main reason we want to, what information am I trying to derive or get out of this I2 versus V1 plot? Y21. So I want to maximize Y21, right? If I want to maximize Y21, where do you think I should be biasing? Where do you think I should be biasing the MOSFET at, or the device at, in this case? For a high value of V1, for a low value of V1, somewhere in the middle? High value, why? Slope higher, right? So as I go higher and higher values of V1, the slope increases. Slope is essentially Y21. We want high Y21, so we want to go toward higher and higher values of V1. We want to bias it at higher and higher values of V1, right? So we would like to bias this side. But do you see a problem? It may go into linear region, because as you go to the right, as you keep on going to the right, it can enter linear region. Okay, so then herein comes the choice of a designer, right? Would you like very Y21 and risk going into linear region, or would you want moderate values of Y21 and stay away from linear region, right? So these are the things we'll see in the classes going forward. Okay. Any questions till now? Okay. So again, let's go back to our black box. So again, you are given the black box where I'm not sketching I21. I am not sketching, not writing I1, but I2 is some F2 of V1, V2, and we know what this F2 is, right? And we also know that the input current I1 is 0. And we also know that we have to bias it with certain voltages, right? So again, let me dig a bit deep on this. What will happen if I forget about biasing and simply say that I will apply my input like this, and I connect load resistance like this. Will this work, given that the black box is the MOSFET? Note that this is total IV, not incremental. Do you see an issue? Is it work? Will it work or will it not work? It will not work. Why? Can you speak up? Voltage is not, which voltage? Input voltage. What is the input voltage? We know that I1 is always equal to 0. So what is the input voltage? It's a VI is small signal, right? So what is the input voltage? Is VI, right? So clearly, as he says that VI is small signal, threshold voltage is, let's say, 1 volt. So your transistor is not even turned on, right? So it's in your I2 will be absolutely 0. So this will clearly not work. So what is the first thing that we need to do? We need to ensure that I establish the proper operating region. When I say establish the proper operating region, which means that we have to decide where in this graph I would like to bias the transistor, right? So from the input side, when I'm trying to figure out what V1, where should I bias V1? So clearly I have to be somewhere between 1 volt to some higher value. Whatever is the higher value is dependent on what? So I have to be somewhere, clearly I have to be this side, but I cannot go all the way to the right also. So how much can I go to the right? What determines that? V2, right? Essentially V2, right? V2 plus threshold voltage, yes, but essentially V2 determines that. So given that, so I need two information. Okay, so I need to understand where should I bias V2 at? Which plot will tell us where should I bias V2 at? The left one or the right one? So the plot on the left is kind of giving us an indication of where should I bias V1 at. The plot on the right is giving us an indication of where should I bias V2 at, given that I would want to get as high a V1 as possible. Right? We want as high a V1 because we want large Y21. Correct? So which means that I should be trying to get as high a V2 as possible, which means I need to be biased at as high voltage as possible. If that is allowed, obviously you will know that you cannot really keep on jacking up the voltages because of reliability concerns and many other reasons. But given we are not getting into that limit as of now, but let's assume that we can jack up V2 as high as possible. Okay, so if that is the case, so let's first establish the bias, then we'll think of the increment. So what is the easiest way to establish bias? So let's start off with V2. And let's say I want V2 to be equal to 3 volt. Right? So which means I'm saying that this is the range of V1 I can play with. So I bias V2 here. V2Q equal to 3 volt. And V1 has to be greater than 1 volt and less than is this thing. V1 has to be somewhere above 1 volt and less than 4 volts. So let's choose 3 volts or 2.5 volts, somewhere in between. So, or let's say 2 volts. It's maths easy. So V1Q is equal to 2 volts. Okay. So now are we convinced that this guy is biased in saturation? Yes. Okay. Great. So now we have ultimately the reason we want to bias the device in saturation is because we want to get some amplification out of it, which means we need to figure out a way of applying the signal in the first place, right? So ultimately in the incremental model, we would want this. In the incremental sense, the incremental picture is this. So in case of a transistor, these two are shorted. So ultimately we want this. This is the incremental picture. So in the incremental picture, when I am applying a V1, in the total picture, what am I doing? What am I implying? Again, let's go back to the curve. So let's say I have biased it at 2 volt. Right? So now I say that in the incremental picture, I want the input to swing. Right? I want the input to be applied across V1. Incrementally, I want the input to be applied across V1. Okay. So what does it say to the total picture? Again, if I go back to the curve, what does it imply? When I say I want to apply the input, but the incremental input will go to directly to V1. What does it say? Where am I located in the curve and which side am I moving? If let's say V1 is, let's say Vi is a sinusoid, right? So where am I located and which side am I moving? I am clearly moving around 2 volts because ultimately we got the GM around 2 volts, right? Or rather Y21 around 2 volts, right? So clearly we are moving around, we are back and forth around 2 volts in order to get an incremental current. Okay. So in other words, we are looking for a V1 which is equal to V1Q plus an incremental Vi. Correct? That's all we are looking for. So now how do I arrange this in circuits? How do I add up 2 voltages? Right? Simple thing to do. If I have access to batteries, I can basically put 2 batteries in series. So I get summation. So if I have a V1, if I have a Vi and RS, this is what I can do. Now, can you comment on what will happen if absolute I1 is not equal to 0? As it turns out, MOSFET is very good device as far as these things are concerned, but let's assume I1 is not equal to 0. Can you comment on what might happen if I connect my network like this, input like this? Why? Great, right? So if I1 were not equal to 0, there would have been a finite I1, which means what? I am drawing current through the resistor also. Since I am drawing current through the resistor, then this RS comes from where? This RS comes from a source, not in your control, right? Previously, somebody has given you an RS. It comes to a source, not in your control, which means that V1Q would have changed from V1Q or from 2 volt to some other value. Okay. So I mean, but fortunately, in case of a MOSFET, in most MOSFETs, it's not a problem. But unfortunately, in modern day MOSFETs, I1 is not 0 anymore, right? So that's a story for another day. But let's assume I1 is equal to 0. So this is good. So I have applied V1. Now, is there anything that needs to be done on the input side? Yes.
I1 will be 0, right? In case of if I1 is not 0, then there will be a drop across R2.
Right. Not R2, RS. Yeah, fine. RS, yeah.
So, but this drop is again sinusoidal.
Not necessarily. This RS is present regardless of Vi is 0 or not.
Even if Vi is 0, RS is present. So in that case, also it will change the.
Correct. Yes. Right. So that is definitely one case. Another case is also the point that you were trying to make. Even in the incremental sense, if I1 is not equal to 0, and let's say even incrementally I1 is also not equal to 0. So then what is the implication? The implication is that I have Y1. correct? So in that case, my whole of V1 will also not drop, will not appear across V1. So it will not be a very good amplifier in that case. Right? Okay, so are you satisfied from the input side, or do you think something else needs to be done? Okay, it's fine. So let's go to the output side. And the output side, we would like to arrange. So let me use the RL in a different color. So we like to ensure that the RL is attached between the ports, right? Between the terminals. So what should we do? Incrementally, at least, we should have RL across the terminals. So what should we do? Any comments, suggestions? Tell me I connect it anywhere. Tell me, where should I connect? Pick up in series with this. Okay. Okay. So why not in parallel? We'll come to series. So why? So let me ask, why? What's the problem if I connect it like this? Right. So yeah, I mean, so incrementally, what is the impedance looking this side? The incrementally, this Thevenin equivalent resistance is 0 because I have a constant voltage source, right? Voltage source shorts, so essentially it's 0. So I mean, in the increment, if I connect it like this, in the incremental sense, this is what is going to happen. Right. So all you will be generating GM times V1 current. There is no doubt about that because the transistor is biased properly. But all the GM times V1 current will flow into the short, and it will not flow into the not flow into the RL. I mean, again, other way of thinking about it is like V2Q, you are holding the port voltage V2 constant, which means you cannot even hope for that port voltage to move. Right. So it cannot be held constant. So you cannot add in series parallel. So next thing to see is series. Let's say RL is 10 kilo ohm. So by the way, if RL is 10 kilo ohm, what is the expected gain that I can have? It's Y21 times RL, right? So the value is Y21 was how much? 2 millisiemens, if I recall. It's 2 millisiemens. RL is 10K. So the expected gain is of 20. Okay. Fine. So now tell me what's going to happen if I connect it like this. So now what is the expected quiescent current if the transistor is biased in saturation, right? Because I have two lesions to deal with. So we have to assume something to start and then see whether that assumption is valid or not. So let's say assume the transistor is biased in saturation because it started off with saturation biasing. So if the transistor is in saturation, what will be I2Q? Can you quickly calculate and tell me, or even look at the plots and tell me? V1Q was in this case 2 volt. 1 milli, right? So this is 1 milli. So now tell me if this is fine, there is an issue. So from the perspective of quiescent points, has the quiescent point gotten disturbed, or is the quiescent point fine? Input quiescent point, has it gotten disturbed? No, clearly, right? Because we don't have any connection between output to input, right? So whatever we do to the output, it doesn't change the input. Whatever we do to the input changes the output, but not the other way around. So we don't have to bother about anything changing at the input side. Has something changed on the output side? Yes, no, no comments. How many of you think something has changed? How many of you think something hasn't changed? Or nothing has changed? No comments. How many of you think no comments? So what is bothering? What is bothering you? I mean, clearly you're thinking, that's why you are fighting with the idea. Yes? Right. So I2Q will drop across RL. Right? So if I2Q drops across RL, if this is in saturation, by the way, we're assuming it's a saturation. If in saturation, the current is not dependent on V2. Right? So again, same old. So if we are in saturation, if we are in this region, then the current is not dependent on V2, right? So we can independently calculate the effect of I without thinking about what's going to happen to V2 if it's in saturation. Because in saturation, it's a current source, correct? I2 doesn't change. So if it's in saturation, then I2Q is 1 milliamp. And if it's in saturation, then voltage drop across RL will be 10 volt. Correct? So now what will be V2? It will be 3 volt minus 10 volt, that is minus 7 volt. So clearly the transistor is not in saturation, right? So then what is the next thing to do? I mean, I couldn't put RL in parallel because incremental picture was not happy. Now I put RL in series, the quiescent picture is not happy, right? So what should I do to restore the quiescent point? Okay, so if I put it in parallel, so in the incremental picture, what's going to happen? Correct. Yes. Yeah, it will always be same as V2Q. So it's a DC voltage across across the RL all the time. You will not get any increment of the voltage. Right? Ultimately, in an amplifier, we want the output to respond to the input change. That's not going to happen, right? So we cannot put that. So fine. So now we have a problem. So what's the solution? So again, when you have a problem, it's instructive to understand why it's a problem. The problem is because V2 has dropped. Right? So I have to increase V2. And again, you have to assume that it's in saturation, right? Ultimately, that is the goal. So if it's in saturation and V2 has to be brought up, what is the only handle that you have in this picture? So V2 is essentially your V2Q, or in this case, instead of saying V2Q, let me say V2 applied, right? So let's say this is V2 applied minus I2Q times RL. Do I want to change I2Q? As a designer, do I want to change I2Q? No, because I2Q has, given that I have put in a lot of fight to find out what is I2Q because I want certain Y21, certain biasing point and so on. I don't want to change I2Q. RL is not in our control. Has been given to you, which means I cannot change this. I2Q times RL, I will not be able to change. I mean, not in your control. So what is the only thing that you can change to raise V2? The quiescent applied voltage, right? So you can change V2. How much do you want to increase it by? If I have to restore V2 is equal to 3 volt, which was initially. So this has to be 3 volt, which means your V2A has to be I2QRL plus 3. I2QRL was 10 volts, so 13 volts, right? So this has to be increased to 13 volts. So if we increase this to 13 volts, V2 will get restored to 3 volts. the voltage across RL is fine. In the incremental picture, you are also good. Right? Make sense? Okay, so let's stop here. We're out of time. Meet in the next class.